Okay, let's get back on to series again. Series with positive, or I should say at least non-negative terms, okay? Non-negative series. And today we're going to look at things that are similar to the geometric series. Recall the geometric series. Something of this form, r to the n, which is 1 plus r squared, you go all the way out. And that ends up converging. We not only know it converges, but we know what it converges to. It converges to 1 over 1 minus r if r is less than 1 in size, and it diverges if r is greater than or equal to 1 in size. Okay, so that's the geometric series. And we're going to use that to motivate a way to be able to solve lots of other series. It's called the ratio test. It's kind of a cool test. I think it's one of my favorite ones. You'll see why as we do it. But before we get into it, let me just remind you of something. We know that things like 1 over the square root of n diverges. Why does it diverge? The terms go to 0, but they don't go to 0 fast enough, right? These don't go to 0 fast enough. On the other hand, 1 over n squared or 1 over n to the 200th power, for sure, those are going to converge because they not only go to 0 fast, this n to the 200th power goes to 0, gets big really, really fast. So 1 over that gets small very, very fast. And what I want to show you very clearly is that anything that's like this, like a geometric series, these are going to get small. If they do converge for r less than 1, they are going to get small much, much faster than anything like this. Okay? Basically, if you take any number like, let's just take a simple one. Let's take 1 over e. Okay? I'll show you why it's simple. 1 over e, do you agree that that's less than 1 in size? And so, of course, this thing right here is equal to 1 over e to the n. And so the point is, this thing converges because the e to the n gets big much, much faster than even anything like this. How do you prove that? Let's go ahead and do it. We'll stick in x's there so that we can take the derivative. Do you see where I'm heading? Why would I want to take the derivative? E to the x. As x goes to infinity, goodness, for you know, if you let x equal 1, 2, 3, 4, 5, this thing's going to be much, much bigger than this. But give it a little time. As you go out farther and farther, what happens as you take the limit of this thing? Notice it's of the form infinity over infinity, so we can use L'Hopital's rule and take the derivative of each one. If you do that, you're going to get 200 times x to the 199th power all over e to the x, and that's still of the form infinity over infinity. So we haven't helped ourselves much, but you can pretty quickly see what's going to happen if you use L'Hopital's rule 200 times. Use it 200 times, and you're going to end up with 200 factorial on the top. That's 200 times 199 times 198 and so on. And on the bottom, it's just going to still stay e to the x. Agreed? So now that you have this is a huge number, but it's a fixed number. And this thing here is going to keep getting bigger and bigger and bigger. So that ratio is going off to 0. So that shows you that e to the x grows faster than anything like this, which means 1 over this is going to get small much faster than anything like this, okay? So whenever you're dealing with anything that's kind of like the geometric series here, if it's getting small, it's getting small really, really fast. If it's not e there, any number r, as long as r is less than 1 in size, like this is less than 1 in size, that's going to get small very, very fast. On the other hand, if you look at the geometric series, the reason this thing diverges is because these things aren't even going to 0. You take a number bigger than 1 in size and you keep multiplying it by itself, and these are going to get bigger and bigger and bigger. So the geometric series is kind of all, it's extremes. Either it converges very, very quickly, or else it diverges because the terms don't even go to 0. So it's kind of extreme one way or the other. Okay. So now, with that as kind of an introduction and rehash of the geometric series, let's look at another way of thinking about this that's going to generalize. Let's let our a sub n be equal to r to the n. That's this particular series. I've got that. And so, given that, I'm going to rewrite the way I've got this expressed. Watch this. I'm going to take the n plus first term in the series, a sub n plus 1, and divide that by the nth term, which is simple enough to do. If this is my series, that's just going to be r to the n plus 1 all over r to the n, agreed? And that just simplifies to r, agreed? R to the n plus 1 divided by r to the n is just r. So another way of writing what happens to the geometric series is to write this. It's to say if the limit of the n plus first term over the nth term as n goes to infinity, which is just going to be the limit of r as n goes to infinity, and r is just a constant, that's just equal to r, that as long as that thing is less than 1 in size, notice we don't have to worry about this being negative because all of our terms are non-negative here. If this thing is less than 1 in size, then the geometric series converges. Agreed? So I just took something that looked pretty simple and I made it look very more complicated. I already know the result. I know that the geometric series converges as long as r is less than 1 in size. But instead of just saying r, I got my r by taking the n plus first term divided by the nth and then taking the limit of that as n goes to infinity. Why would I want to do that? Okay, can you think of any reason? Well, the reason is because this idea generalizes to other things. So suppose I've got this series now, a sub n, where again the a sub n's are greater than or equal to 0. And let's do the same thing I did right here. Let's take the limit as n goes to infinity of the n plus first term divided by the nth term, and let's say that limit is equal to r. Okay, let's say it's equal to r. And here's what we're going to conclude. We're going to conclude this thing converges if r is less than 1 in size, and this series diverges if r is greater than 1 in size. Same as the geometric series. Okay, that was true for the geometric series. The geometric series, if r is less than 1, it converged. If r is greater than 1, it diverged. And the same thing is going to be true of any series like this. And so basically, here's basically what we're saying. We're saying that this series here, let's just kind of see once what's happening. If you take this and you just say, okay, in the long run, this thing here is equal to r, that really kind of means that a sub n plus 1 is equal to r times a sub n. So it's basically saying that you get the next term in the sequence in the long run by just multiplying the previous term by r. So in other words, these things are going to be being multiplied by r, and if r is less than 1, it's going to be acting very much like a geometric series. Each one is only going to be r times the previous one. So you keep dividing it, or you keep multiplying it by a number less than 1 in size, and so these things are going to keep getting smaller and smaller and smaller as long as this r is less than 1. See that? So that's the idea of the geometric series of this, called the ratio test, because we are taking the ratio of consecutive terms. And as long as the ratio of those consecutive terms is equal to r, which is less than 1, that means that each one of these things is basically going to be less than the previous one, at least in the limit. So that's the idea. Okay, the proof is just kind of just going through the details of that. Okay, now notice that this is, I call this an intrinsic test. Intrinsic test. Intrinsic means it's internal versus an extrinsic test, which is kind of external. So an extrinsic test for series would be to show that this thing, for example, converges. Why do we know that converges? Because we compare it with this integral, and we know that this integral converges by techniques of integration, and that actually converges to pi over 2. That's your arctangent. And so since this thing converges, we can compare the area underneath these rectangles with this area, and we say that this thing converges. Or you could do what? You could go like 1 over n squared plus 5n plus 7, and you can say, oh, I know that n squared plus 5n plus 7, that those are going to be less than or equal to 1 over n squared. And I know that this series here converges by the p-test, which is basically by comparing it to an integral. And so since these are all less than or equal to these, that means that this one here is also going to converge. Okay? So these are all extrinsic tests. You're comparing it with something else that you already know. Okay? And this one here, the ratio test, is an intrinsic test. You don't have to compare it with anything else. You're just comparing the individual terms of the series. Okay, so let's see how this works. Okay, let's see how this works. So let's try this one. How about let me see what I have written down here. 2 to the n over n squared. Okay, let's look at that one. N will have to start with 1 here, obviously. N can't be 0. So what's going to happen to that in the long run? Okay, well, let's use the ratio test on it. The ratio test says I look at the limit as n goes to infinity of the n plus first term. So every place I see an n, I put an n plus 1. See that? And then divided by the nth term. Here's the nth term. There you go, right there. And so that's always the first step. But after you've done 2 or 3 of these, you can skip the first step, because the next step is always to flip it up and flip it over and multiply, right? So I can write that as n squared over 2 to the n. Okay, so after a while you just skip that first step and you go right to this one. And then you can, if these are all being multiplied, you can connect the line there, and it's just all this stuff right there. There it is right there. Now it's kind of like cleaning a fish. You want to get all the junk off a fish and be left with just the good stuff that you want. And the same thing here. You do a whole bunch of dividing basically and canceling, and you get rid of all the junk and you see what you're left with. So let's see what we're left with here. First of all, notice I have one more factor of 2 up here than I do down here. So that goes with this, and I'm left with a 2 up there. See that? So that's what I mean by cleaning the fish. You get rid of all that stuff. Here, there's nothing I can really get rid of, but I can write it like this. N over n plus 1 quantity squared. And now I know that as n goes to infinity, this inside here is going to go to 1. Everyone agreed? That's going to go to 1. You can divide both the top and the bottom by n if you need to, but the highest power is the same on both the top and the bottom, so that goes to 1. 1 squared is 1. 1 times 2 is 2. So that's equal to 2. 2 is greater than 1. So we know that this thing, by the ratio test, diverges. Okay, it diverges. So there you go. Okay? And notice again, as I said before, it diverges. Why? Because these terms here are getting big much faster than these. Basically, each term in this sequence, in this series, each term is twice as big as the previous one. So of course it can't converge to a finite number, because the individual terms are not going to zero. They're not only not going to zero, they're getting bigger and bigger and bigger as you go. See that? So so that thing had no chance of converging. Okay, so there's that one. Let's change the bottom here and make this n factorial. Okay, n factorial. By the way, 0 factorial is defined to be 1. So this one I could start with 0 here. Okay, so let's do it again. Here we go. As I say, these are kind of fun. Take the limit as n goes to infinity. Take the n plus first term, 2 to the n plus 1, divided by, every place you see an n, you have to put an n plus 1. So you get that right there. And now you do what? You multiply by the reciprocal, so it's going to be n factorial all over 2 to the n. Be careful with your writing here. You always want to write limit as n goes to infinity. Let's clean the fish, get rid of as much as we can. So this 2 to the n can cancel out with a whole bunch of these, with n of these, and I'm left with just one of them left. So we've got a 2 right there. Notice here I have n plus 1 factorial, and here I have n factorial. Let's think about this. If n was equal to 5, you would have 5 factorial over 6 factorial. How does that reduce? 5, 4, 3, 2, 1 on the top. On the bottom, you're going to have 6, 5, 4, 3, 2, 1. Those all divide out. See, as I say, all this stuff divides out so nice. All you're left with is a 6. So similarly, here you have n times n minus 1 going all the way to 1. Here I have, in fact, let me write it like this. Agreed? N plus 1 factorial is just n plus 1 times n factorial. Those all cancel, and I'm left with 2 over n plus 1. As n goes to infinity, this thing goes to 0. It's less than 1. That's all we need. So this thing here converges. And again, it converges absolutely. There's no negatives in here, this whole thing. So if it converges absolutely. Okay? So that means that each one of these things is getting much smaller than the previous one. Okay? You're adding up a whole bunch of terms, and the terms are getting small very, very fast. Okay? Are you good on that one? Let's try another one. Let's leave the n factorial down there, and let's put an n to the n up on top there. What's that one going to do? Here we go. Take the limit as n goes to infinity. Again, be careful. It's going to be n plus 1 to the n plus 1 power, all divided by n plus 1 factorial. Agreed? All divided by this, so it's multiplied by the reciprocal, n factorial over n to the n. What can we do with that? Well, let's clean the fish here. I can cancel those with those, and I'm left with 1 over n plus 1 down there. Agreed? I have 1 over n plus 1 there. Now, what can I do to simplify this stuff? Notice I have two things going on. I've got an n plus 1 there, whereas I have an n there, so my base is different. Also, I have one greater power here than here. So let's at least take care of that greater power this way. Let's multiply off one of these n plus 1s, and then I'm left with n plus 1 over n all to the n power. See that? So I had an n plus 1 down here from the factorial. Here's an n plus 1 right there, and I'm left with n plus 1 to the n all over n to the n. And I'm using a lot of algebra here, so this is n plus 1 over n to the n. What happens to this limit? Well, let's see. These things just go away. They divide out. So I'm left with this. And you look at this and you say, well, what's happening here? As n gets big, this inside is going to 1. And in the previous example, I had something like that. Let me just write it like this. I forgot what power I had. I think I had it squared. If this inside is going to 1, 1 squared is equal to 1. So that one there, I just quickly and easily said that goes to 1. The problem, let me make sure my computer is still working here. Very good. The problem is you've got two things happening at once here. The inside is going to 1, which would kind of force it down to 1, but this outside is trying to make it big because it's taking a number that's bigger than 1, slightly bigger than 1, and it keeps multiplying it by itself. So you've got, instead of having this thing out here, which is just a constant, now this thing is fighting with the inside. This thing is trying to draw it down to 1. This is trying to push it up to infinity because it's taking a number bigger than 1 and keeps multiplying it by a higher and higher number. So you've got a tension there. You've got a tension. In fact, if we were to rewrite the inside, notice I can write it as n over n, which is 1, plus 1 over n. That's all to the n power. That would be a way to rewrite that inside. And now, if I ask what does that limit go to, you might recognize it. Back just a couple times ago when we looked at sequences, we played with that one and we used L'Hopital's rule to show that that thing went to E. Okay, so there it is. You have to recognize it when you see it. This thing here is the same as that, and that thing goes to E. So let's just do it right here. There's E. What's important about this? E is greater than 1. E is greater than 1. So since this thing here convergent, since the ratio of the consecutive terms has a limit which is greater than 1, that means that this thing here is going to diverge. And it diverges, there's nothing subtle about it. Each term is roughly E times the previous term. So the terms aren't even going to 0. Okay? Now, if you're an astute listener, you might be looking at this and saying, hey, we have an answer for r less than 1. We have an answer for r greater than 1. What happens if r is equal to 1? With the geometric series, we did have an answer when r is equal to 1. Let's see once what happens with this ratio test here. Okay? Well, let's look at this one. What do you know about that series? Hopefully, as soon as you write that one, as I write that one down, you look at it and say, oh, that's a harmonic series. I know that that thing diverges. They don't go to 0 fast enough. So we know that this thing diverges. Okay, but watch what happens when we use the ratio test on it. We're going to get 1 over n plus 1 divided by 1 over n. So that's going to come up like this. And so that's the limit as n goes to infinity of n over n plus 1, which is equal to 1. So look at here. Here's a case where the limit of this ratio here is equal to 1, and sure enough, this thing diverges, just like the geometric series. See that? So can we just go ahead and say that? I've got a question in my voice. Hopefully you're just being a little bit skeptical if you've gotten to know me through these videos at all. Okay, let's try another one. That one there, by the p-test, we know that this one converges, right? That one converges. However, if we use the ratio test on it, watch what happens. You're going to get 1 over n plus 1 quantity squared divided by 1 over n squared, so that's going to bring the n squared up like that. And that's going to be the limit as n goes to infinity of what? N squared over n plus 1 squared, or I can write it as n over n plus 1 quantity squared. And now it's the same sort of thing we had before, but now this inside goes to 1, and you've got a fixed number there. So that's not going to fight with this one. It just has no choice but to go to 1. So what's our conclusion? Notice that things can either diverge or converge and have the ratio be 1. See that? So the point is, this is all we can say, okay? If you use the ratio test and you get a ratio of 1, then you don't know the answer. You're going to have to use some other test or try something else, okay? It's inconclusive, okay? So that's the idea. Okay, let's try one other one just for the fun of it. These are all, as I say, they're all kind of fun. Let's try this one instead. Put a 4 to the end there. What happens if you have a 4 to the end? In fact, here, let's really spice it up. I'll write it as 3 to the n. What else did I have there? N factorial. And n to the 50th. Okay, show you how messy these things can be. Okay, here we go. Take the limit as n goes to infinity. So here we go. It's going to be n plus 1 to the n plus 1 power all over 3 to the n plus 1 power times n plus 1 factorial times what? N plus 1 to the 50th. Okay. Now it's going to be divided by the other thing. So everything out, now I got to flip everything over and put them in the numerator. So it's going to be 3 to the n factorial, n to the 50th, and then n to the n. Down here, right? N to the n. Okay, so let's see if I can get one more thing on this line here before we go underneath. Here we go. Are you with me? First of all, we're cleaning fish here. I just like this as cleaning fish. It's not that I like cleaning fish, but I do enjoy this. These all divide out with this, and I'm left with a 3 there. Okay? Here I have n factorial. Here I have n plus 1 factorial. So they all go away, and I'm left with an n plus 1 there. See that? Here, I can factor out an n plus 1, and after factoring out the n plus 1, then I can write it as this thing to the n over this thing to the n, which I can write as n plus 1 all over n to the n. So that takes care of all of these and all of these. And finally, I can combine these things together, and I can write it as n over n plus 1 all to the 50th. See that? So here you go. What happens? The 3 stays there. These go away. What about this thing? N over n plus 1, that goes to 1. 1 to the 50th power. 50 is fixed. It's just going to be 1. It's just going to be 1. So that just stays 1. And this thing, you recognize this from before? That thing there goes to E. See that? So what do we have as a result? E is less than 3 in size. So this thing here is going to be less than 1. And since that's less than 1, we know that this thing is going to converge. See that? That one's going to converge. Notice that if I had made a 2 down here, then I would have had a 2 down here, and E over 2 is greater than 1, so then the answer would have been, it would have diverged. See that? So, so there you go. So, so that's the ratio test, and in the next video we're going to see another way of kind of generalizing from the geometric series. It's called the root test. Okay, it's the same sort of thing. Okay. These are 2 cool, very cool intrinsic tests. Very good. See you next time. Okay, I could have continued this on to the last one, but I want to make it separate just so you kind of have a clear distinction between these 2 tests, although they're very similar. The second one, I left a lot of the stuff up here from the previous lesson, is called the root test. Instead of the ratio test, it's the root test. And basically, we get the root test kind of in the same way that we got the ratio. We look at the geometric series and we say, how can we get an r out of that? One way we got an r was by taking the n plus first term divided by the nth term, right? If you do that to the geometric series, you get an r. And then we know that if r is less than 1, it converges. If r is greater than 1, it diverges, okay? Another way you can get an r from the geometric series is by taking this instead. So instead of taking the ratio, we take the nth root of the nth term. Agreed? If you take the nth root of the nth term of the geometric series, you're going to get an r. And so here, again, you take the nth root of the nth term of r to the n, and you're going to get an r, and you get the same result as before. And that leads us to another way to generalize the geometric series. We look at that and we say, okay, let's take the limit of the nth root of the nth term, and if that is equal to r, then the same result as before, for the same reason. If the series converges if r is less than 1, and it diverges if r is greater than 1. And again, this is an intrinsic test. We're not comparing it with anything else. We're just looking at the things themselves. And so that's the root test. So as an example, we could do one that we could use it on the geometric series if we wanted to. Here's the geometric series. We know that this thing is going to converge by the geometric series, but if I use the root test on it, what does the root test say to do? It says I take the nth root of this nth term, and of course these two n's, you take the nth root of something to the n power, and they just undo each other, and you're just going to get 2/3, and 2/3 is less than 1, and so this thing converges, as we already knew. The ratio test was especially nice whenever you have factorials, because factorials, the root, if you take the nth root of a factorial, that doesn't lend itself to being solved. But where the root test is very nice is if you have something like this. Here's an example of something, say 2n squared plus 5n plus 8 all over, I don't care, 3n squared plus 10 plus 10n plus 7, something like that, all to the nth power. All to the nth power, okay? So, first of all, you should be able to guess at what the answer to that is without even doing it, because let's just think about it. As n gets big, this whole inside is going to get closer and closer to 2/3. Agreed? It's going to get closer and closer to 2/3. And we know that if you just take 2/3 to the nth power and keep taking powers of that, that's going to converge by the geometric series. And so you look at this, you say, hey, kind of in the long run, this is really kind of a geometric series. It's really going to be things of the form 2/3 to the n. And what the root test does is just to kind of formalize that idea. So let's just go ahead and do it. If you take the nth root of this nth term, okay, what are we going to get? We're going to get 2n squared plus 5n plus 8 all over 3n squared plus 10n plus 7 all to the nth power, and you take the nth root of that, and that's just going to give you the insides out, of course. So you're going to get 2n squared plus 5n plus 8 all over 3n squared plus 10n plus 7. And now as n goes to infinity, you can divide both the top and the bottom by n squared. And when you do that, this becomes a 2. Here you're going to get something over n. Here you're going to get something over n squared. Here that's going to go away. You're going to get 10 over n, 7 over n squared, and all this stuff goes to 0. boom, boom, and you just get 2/3. 2/3 is less than 1, and so that converges.